Rotations. Perfect. Third type of transformation. So we're used to seeing rotations in real life. Rotations occur quite frequently, but especially with windmills and things like that. All right. So a rotation is another type of transformation, and we define it as a rotation of x degrees about a point r. That point r is called the center of rotation. And it, like a translation and a reflection, is a transformation. Also, like translations and reflections, a rotation is a rigid motion. So remind me, what is a rigid motion? Rigid motion. When you think of motion, what do you think of? Something moving, okay? Rigid, what does that mean? Rough, doesn't change, doesn't give. So a rigid motion is a figure that has moved without changing size, shape, angle measures, lengths. They stay the same. So when you are graphing rotations, you should get the same figure again. If it looks different than its original and its pre-image, then you've made a mistake. All rotations are clockwise by default. So in a digital age, what does that mean? You guys don't usually use an analog clock. What does clockwise mean? Goes the way of the clock, right? These will be very good. So you watch the second hand on a clock, and that's clockwise. Unless we tell you otherwise, when you're doing unless we tell you otherwise, every rotation that we're talking about is a counterclockwise rotation. Opposite the clock. Counterclockwise. So you have an image on your paper. I'm not talking while I'm talking. I'm tracking the speaker, you're paying attention. So you have a figure. That figure is a triangle. You have a triangle on your drawing or on your paper, and it has a point R that we are rotating about. We are rotating x degrees. When we rotate x degrees, v and moves to v prime, u to u prime, w to w prime, just like before. The distance between your point of rotation and v prime is the same as the distance between your point of rotation and v. Likewise, that r to u, the distance between r and u, is going to be the same as the distance between r and u prime. So they're going to maintain that same distance away from that point of rotation. Okay? So we're turning everything counterclockwise a certain amount. And this r, distance between r and w, will be the same as the distance between r and w prime. Okay? Likewise, the pre-image of v and v prime are equal distances from that center of rotation. So we have some coordinate rules for rotations, just like we did for reflections. Those coordinate rules about the origin, if we're rotating around the origin, the point 0, 0, are for a rotation of 90 degrees, point A and B are now going to be point negative B, A. So what did they do? Switched the x and y and made the new x the opposite sign. Okay? So you can switch the x and y and make the new x the opposite sign. For a rotation of 180 degrees, AB is now negative A, negative B. Exactly. We just changed the sign. So if it was already positive, it's now negative. If it was negative, it becomes positive. We're just switching across the line y equals negative x, aren't we? We're reflecting. Okay. So the third one is the rotation of 270 degrees. AB is now going to be negative A. Switch them and negate the y. Yep. Switch them and change just the y. So this one is like the inverse, isn't it? We negated both. Okay. But the other ones don't follow those patterns. All right, so we're going to find the coordinates of P. P was 2, 3. And we want to rotate that 90 degrees about the origin, about 0, 0. Negative 3, 2 if you follow the coordinate rules. We switch the two, the x and y around, and we negate the new x. So put a point at negative 3, 2. Label it P prime. It's going to be a negative 3, 2. Our original point was here. Here's our angle of rotation. We're 90 degrees away. Yeah, it's supposed to be. It may be scaling improperly because of the projector. Okay? And these two distances should be the same length. Okay? So those coordinate rules can help you. Okay? The coordinate rules can help you. Would you like to see another way? Okay? Another way of doing this? Okay? Here's our coordinate again, 2, 3. We know it's going to go to negative 3, 2. Watch what happens when we rotate. Everybody watching? Okay? Turn your paper sideways. Decide where it's at. Negative 2, negative 3, 2, right? 3 back, don't look at the numbers. 3 back, 2 up. That's where our new point's going to be. Okay? Just rotate your paper, figure out where it will be, then rotate it back and plot that point. Both ways work. P prime. Yep, when we turn it, watch what happens. It ends up in the same spot. Okay? So you can rotate your paper, ignore the numbers. They're going to be sideways and backwards, right? And just count your blocks. Figure out where it's going to go, turn it back, and plot your point. Okay? So try that with this one. You can either use the coordinate method, or you can try by rotating it. We have triangle ABC. We want to go 180 degrees. 180 degrees which way? Counterclockwise always. Okay? 180 degrees counterclockwise. So my point, I'm currently at, B is at 4, 4. A is currently at negative 3, 5. and C is currently at 0, 1. We rotate it 180 degrees. Yep. Okay. So A prime is now going to be at 3, 3, -5. So 3, -5. Let's make that in a different color. B was at 4, 4. It'll be -4, -4. Yep. B prime, we negate them both. So it was at 4, 4. Now it's going to be at -4, -4. And then our last one, C was at 0, 1. So it will be at -1, 0. And provided we use a ruler, we'll get nice, neat lines that look right. And I did that wrong. Should be at 0, -1. My fault. Apologies. We don't switch it, we just change the sign. Okay? Everybody get the same thing? Quentin, Sam. Everybody get the same thing? Okay. Uh-huh. Yep. That's perfect. Yep. Now make sure you label A prime, B prime, C prime. Okay? Yeah, it should be +5, 3. Five, -3. Let's see, we're switching the, no, should be negative, should be 3, -5. Okay? Okay. So here we go. Find the coordinates of the vertices of ABC. Now be careful with the directions here. This time they're saying go 90 degrees clockwise. So they're breaking our rule. They told us you have to do it the opposite way now. Okay, so we're going 90 degrees clockwise. This time we're going this way. So let's turn our paper. So we practice that skill. When you turn your paper, the new A will be, don't look at the numbers, 1, 2, 3, 4, 5 over and 3 up. 5 over, 3 up. That's where your new A will be. 5 over, 3 up is your image, A prime. Now we're taking B. Okay? Rotate your paper. It'll help. So, okay, so when you rotated your paper, we're now at a new location. And don't look at the numbers. We're 1, 2, 3, 4, 5 over, and 1, 2, 3 up. Okay? So when you turn your paper back, put it at 5 over, 3 up. 5 over, 3 up. Okay? Now watch when I turn it back. Okay? B was at 4 over 4 up, right? When I rotate my paper, now I'm at 4, negative 4. Okay? Where was I? Okay. And C was at 0, 1, right? So we rotate our paper, and we're at 1, 0. Yep, 1 over 0 up. Okay? This was 90 degrees clockwise. Okay? 90 degrees clockwise. So when you do it, yeah, you did. So when you turn it, you only want to turn it this far. No. Which one were we on? Actually, you want to turn it this way. So we were here. B is now going to be this far over, this far down. Okay? All right, here's the next one. Rotational symmetry is if you have rotational symmetry for a figure, if there's a rotation of 180 degrees or less, for which the figure is its own image. So you rotate it 180 degrees or less and you get the image back, that's called rotational symmetry. Okay, so a figure has rotational symmetry if we can rotate it 180 degrees or less and you get the figure back. So you have an example of a parallelogram, a quadrilateral, with two pairs of parallel sides. And it has a diagonal going across the middle. This has 180 degree rotation, rotational symmetry. So watch what happens when we rotate it. Everybody ready? Eyes up here. AJ, eyes up here. Here we go. So watch it. Okay? Turn it 180 degrees and we get the same figure. Okay? This triangle will also have rotational symmetry. Okay? But unfortunately, it's 120 degrees, and PowerPoint likes to do things in 90, 180, 270, 360. So you have to trust me on this one. Okay? It won't rotate exactly. It won't. I don't have the rotation going. Okay? So, and the reason is, what kind of a triangle is this? Equilateral. Very good. Okay? Equilateral means all three sides are equal. That forces the angles to be equal. And that's what makes it have rotational symmetry. Okay? How about this one? Will this have rotational symmetry? Yes. Okay. Everybody agree? Let's try it and see. We put a point A out there so that we can watch it and know which way it's going, or where that particular vertex is going. So there's 1, 2, 3, 4. Yep. 5 rotations before it gets back to its original place, right? But it was the same figure 5 times over. So how many degrees of rotational symmetry does this one have? 360 divided by 5. 360 divided by 5 is 72. So when they ask if a figure has rotational symmetry, you say yes, and you tell us what type. This one has a rotational symmetry of 72 degrees because it has 5 equal parts, okay, and 360 divided by 5. Its angle of rotation is 360 divided by 5, 72 degrees. We know a whole circle is 360, so if it's 5 equal parts to it, that makes sense. A square would be 360 divided by 4. Okay? We're going to look at this later. Okay? So just kind of put it in your mind for something to think about for the future. We'll talk about the figure mapping itself to it, or mapping itself to itself. Okay? How about this one? Rotational symmetry? Why not? Yeah, it's not equilateral, is it? Okay? So it doesn't look the same until it gets back to the start. That's more than 180 degree turn, so no rotational symmetry. Okay? Your assignment's at the bottom of the sheet. Lesson 4.3, page 194, 7 to 26, and 40 to 41. 7 to 26 all.